Hi, welcome to the Signal Path. I got another repair episode here for you guys. We're going to try and see if we can fix one or two of these Agilent 8449Bs. Now you can see the bottom one is HP brand and this one's Agilent brand, so there's a difference in the time where these two were manufactured. Now these are 1 to 26.5 gigahertz preamplifiers, 30 dB gain, intended to be used as a front-end stage for a 26.5 gig spectrum analyzer. These used to be very expensive, and the MXA that I have, the MXA-B that I have in my lab, which you've seen me use in various experiments, has one of these already built into it, essentially because it has a preamplifier for the full 26.5 gigahertz band, except that it goes even lower in frequency. This one starts at 1 gigahertz. Now, none of these work. Now, unfortunately, the chances of us being able to fix one of these is fairly low, especially if the problem is in the amplifier module itself, because it's just essentially just one module, and if it is dead for whatever reason, perhaps too much input power or some weird ESD condition has happened, if that is dead, then there's really not much we can do about it. But nonetheless, I think taking it apart and taking a look at the module will be a good learning experience. And the other part that might fail is the power supply, of course. So we're going to try both of those. Now I'm not going to turn them on and try them on before we open them, because I don't want to turn it on if in case the power supply is the issue to cause any further damage. There's also some bending here on the front panel. Obviously these things have been dropped on their connector side somewhere, maybe when they were thrown out in the trash or something. That's what's happened to them. So we're going to go ahead and take a look. The fault with them is that they simply do not produce any output, or they produce very little output, which unfortunately could mean the amplifier is dead. So let's go ahead, take them apart, take a look inside, and we'll take it one step at a time. And here's a look inside the unit. I chose to open the Agilent one first, the newer one, but I suspect that they're essentially identical. We get rid of this thing here. So that's just to protect you from not getting zapped from the live terminals. You can see multiple windings here because you can choose 110 or 220 volt selection switch over here. Nothing really unusual about the transformer. Multiple outputs because we have a dual power supply. Now it's important to note that this is a 26.5 gigahertz 30 dB amplifier. So with so much gain, you really want a very clean power supply. And 30 dB gain is quite reasonably high, especially at all the way up to 26.5 gig. And even though it starts at 1 gigahertz, you definitely don't want any noise injected into the output of this unit. So switching power supplies are essentially out of the question, and I don't care about the efficiency of the power supply as long as they get a clean supply to the preamplifier module. And that's exactly what they've done. We've got a two symmetric plus and minus linear regulated power supplies over here. The output of the transformer directly goes over there, and because you have two different windings, you can have isolated supply coming out with a common ground in the middle. You can see the symmetry of this power supply, the capacitors, the two transistors, power transistors on the other side of the board. You can't see them, but you can see the footprint on this side. They're connected to a heatsink on the other side, again, because it's going to dissipate quite a bit of power for a linear power supply. Now we can measure these voltages and see what's going on. Now here's the preamplifier module. You can see multiple decoupling capacitors and terminals connected. It's almost certainly a distributed amplifier, most likely in gallium arsenide. I have to open it up and take a look, but we can take a look at it if it's broken. And if this is dead, there's unfortunately nothing we can do about it. And this is most likely the cause of the failure. But I think looking inside this will be pretty interesting. Now we can measure this very easily. That's not a problem. Two potentiometers here to adjust the voltage in case they drift over time. And then we can take a look at that as well. But really, other than that, nothing unusual. The power supply directly going to the module. This other cable you see here going to the front panel is just an LED to let you know that you have turned this unit on. So why don't we go ahead and take a look and see if the power supply works. Now, by the way, there's a manufacturing date in here, 1/23/2001. So it's reasonably old. I wonder what the manufacturing date of the HP one is. And tell us some differences between them. So let's go ahead and plug it into the isolation transformer. All right, the isolation transformer is set to 20 volts, so we can do some quick measurements just to make sure that we have voltages coming to the transformer, so the unit's been turned on. So do we get some voltages between some of these terminals? Let's see, there it is. Okay, so the voltage is definitely getting to the transformer. That's good. Let's measure the output of the transformer. Do we have a symmetric output? There goes 1.4 volt AC coming from here, 1.4 volt AC coming from there. Yeah, definitely producing voltage on the other side of the transformer. So there's at least some division going around there. So let's crank this back up. Let me turn this off for a second. Let's go all the way to 115 where it's supposed to be. And then we can go ahead and then take a look and see if the LED light turns on. Here we go. Well, the LED light is on. That's not a good thing in this case because we want the power supply to not work, but I have a feeling that it does work. So here's the DC voltage on this side, 5 volts, that's spot on. And on this side, -5. Well, it's supposed to be -6, but I don't think that matters that much. So, well, this one's power supply is working, so most likely it's not the issue. I'm going to go ahead and adjust that to minus 6 volts anyway, but looks good. So let's try the same thing on the other unit just so that we are doing parallel testing. I also went ahead and adjusted this one's power supply just so that it is exactly where it's supposed to be based on the specification. So I got one of them to be at 6 volts and the other one to be at minus 5 volts. That's what the spec requires. So it was 1 volt off, which is significant, but it shouldn't really break it to produce no output at all. It'll have to be really power supply sensitive for that to happen. So there it is. It is set, and let's go ahead try the other one now. All right, here's the other unit, and it looks identical except for these sweet red potentiometers. Doesn't have a date, but I see the date because some of the ICs to be in 98. So they're not that far apart. Exactly the same module over here, and we can do the same test and see if the power supply is working. I have a feeling that it probably does. I don't see why these power supplies wouldn't work. Here it is, the other one, and we see 5.9. This one's actually to spec almost. And at the minus, we have minus 9.8. Yep, so the power supplies definitely work, and we can measure them right on the module too. There you go. And there you go. Well, that's not a good sign. And this is problematic, as we say the least, because that means that the module itself has an issue. So, well, there's only one thing to do. We have to go ahead and now try it on the spectrum analyzer, now that we know that these modules actually work. Now, the other one that was 1 volt off, maybe we can get something out of that. Either way, I think it would be interesting to see what's inside these modules and see the condition. Perhaps we can even see where the failure has happened. And here is our setup for checking to see if these amplifiers work. Now, I needed a 26.5 gigahertz synthesizer, but I don't have a 26.5 gig synthesizer. I have a tracking generator. Now, this unit does provide a fairly good amplitude leveled output, but it's not synthesized. So when you set it to a frequency, it's going to be off by a couple of hundred megahertz. It needs an LO input, a sweep, blanking and trace and all the other things that is required to actually become the tracking generator of a 26.5 gigahertz spectrum analyzer. Now, this is not compatible with the MXA. MXA doesn't have an LO out, so I can't use it with that, but doesn't matter. It's going to give us what we want. So right now it's set to minus 30 dBm at 1 gigahertz, which is the beginning frequency operation of the 8449B. And this is the HP one, the one with the red potentiometers, the second one that I tested. So we're going to start with that because it had already good biasing to begin with. The other one I adjusted the biasing on, so we'll go to that afterwards. So let's go ahead and zoom here. I'm going to look at the MXA. So that basically is very simple, going from the output directly to the input and from the output of this directly to that. Now, this is supposed to have 30 dB of gain, as I said. So I'm set this to minus 30 dBm, so we should see about 0 dBm coming out of this. And this is about a couple of dB amplitude levels, so expect a few dB of variation. And this itself actually has quite a bit of variation allowed to be within the operation from 1 to 26.5 gigahertz. We'll take a look at the datasheet, but let's see if anything is coming out. I think I'm going to readjust the camera so we can look at the screen. Okay, let's go ahead and see what happens when we turn the amplifier on. So right now it's turned off, and I'm going to turn it on, and there it is. And you can see we do get some increase in the noise floor coming out, and that's normal for a 30 dB gain amplifier, although this one probably isn't working. But if the later stages are working, you would still get this increased noise floor, and from that you can actually calculate the noise figure of the amplifier. So this is a multi-stage amplifier. That's why I'm saying it doesn't matter if, for example, if the input is dead, this would still happen. So you can see at the very low frequencies, we do have some ripple here. It's not very well matched, and we do have some peak coming out, and this is at 328 megahertz, which is below the 1 gigahertz starting frequency of the specified range for this, but it is putting out more noise at that, which is interesting. Perhaps it's not very well matched at that point, and the noise is just getting picked up a little bit more. But maybe you would need a good high-pass filter after this if you really want to get rid of that. Either way, it's below the spec. So let's go ahead and see what happens if I turn the source on. So the source right now, I'm going to set it to 1 gigahertz and turn it on, and oh, there it is. There's a 1 gigahertz signal, but it's at minus 35 dBm. So this is actually showing some loss at that frequency. So definitely not working at 1 gigahertz, and it's supposed to have 30 dB of gain roughly. So let's go ahead and increase 2 gigahertz, 3 gigahertz. So we're getting a little bit higher signal as we go up, and this can happen. You have more leakage through the first stages of the distributed amplifier, and the later stages might be working, and that's why you're getting. So it's most likely the input is damaged on this distributed amplifier module, but we can keep going. And there you go, it's at minus 20. So we're at 15 gigahertz, putting in about minus 30 to minus 33 dB. We're at minus 20, so it does have 13 dB of gain at this higher frequency. So let's go to 25 gigahertz, And here at minus 19, again, we have we have about 12 or 13 dB of gain. So, yep, it's not working. This is not how it's supposed to behave. So let's go ahead and put the other one in where I adjusted the power supply and see if it's exactly the same or if it has a little bit more gain. All right, here is the Agilent one. So we do exactly the same thing. Right now the amplifier is turned off. I'm going to zoom in here so we can go ahead and turn the amplifier on. Here we go. And there it is. You can see it behaves very similarly, similar issue at the low frequency. So this is a typical behavior. It's unlikely that they fail exactly the same way. And the noise similar as well. So let's go ahead and turn the signal on again at 1 gigahertz at minus 30 dBm input, and well, minus 17. That's a little bit better, but still too low because it should have much more gain than that. So right now it has about 13 dB of gain, so that's not quite good. Let's increase the frequency again. At 2 gigahertz, oh, it's much higher. 3 gigahertz, 4 gigahertz, 5. Oh, let's go. It's going up much better. Yep, you can see that it is working much better at higher frequencies. There you go. That's 30 dB of gain right now. So it does have 30 dB of gain. This is at 15 gigahertz. Now it has even more. Yep, it is working at higher frequencies. That's interesting. It's interesting that the failure is so bad at low frequencies. I wonder if the cable is, the connection is bad. Let's go back again down. Yeah, there you go. So right now at 2 gigahertz and 1 gigahertz. Yeah, it's not working very well at 1 gigahertz. So let's go and investigate a little bit more. I can go ahead and try and wiggle some of the RF cables. See if that makes any difference. Because if it's not working at very low frequencies, it could mean that there's a capacitive connection because the connector is bad. And that could cause this. But I'm moving it around and I don't seem to be able to make any difference. So one other thing we can do is measure the difference in the voltage on the two modules between the two amplifiers. Since we know the power supply is working and there's an array of biasing on those modules, which we can at least compare between the two of them to see if they're identical or not. And then I can also remove the cable and directly connect to the module and bypass all the front-end connections just to make sure 100% that this is not an artifact of something having gone wrong in there. So let's give that a try. So this is what I did. I just connected two SMA cables directly to the input and output of this module, and then these two blue cables go to the same places as before, the output of the synthesizer, the input of the spectrum analyzer. Now technically speaking, you're not supposed to do this because these connectors are K and these cables are SMA. Now, even though they are thread compatible, they're not tolerance compatible. So this is not a really good thing to do. So if you're doing the same thing, well, don't do the same thing. And use actually proper connectors. But I didn't have a right angle connector or a cable to use, which was K, which would fit in that space, and I didn't want to take it out anyway. So I did it this way. But let's go ahead and take a look at the screen. I'm going to turn the instrument on again. I'm going to turn the amplifier on again, but not the source. So we can do the same thing. Here it is. And check it out. Now this is very interesting. You see, we don't have that ripple anymore. That tells me something. It means that there might have been some problem between the connection of the amplifier to the source. And that ripple was because it was really poorly matched at low frequencies, and so the noise was shaped by the fact that the VSWR was so bad and varying between the interface of the amplifier and the output. So this is exactly what we might have just solved by removing those cables, and these are the two cables that I removed. These two cables. We'll take a look at this in just a second. But this interface from here to the front and from here to the front, remember these guys look like they had taken some mechanical damage being pushed in, and I thought maybe that damage is there. So this is very interesting to see that indeed we have a much better response at lower frequency. There's still a bit of a peak there, but I'm not using a very good cable right now. So that's interesting. So let's go and turn the power on. Now I have that 1 gigahertz. We used to have loss there. Let's see what happens now. And check it out. Now this is promising. Look at that. 6 dBm coming out for minus 30 dBm in. So the amplifier is actually fine, which is really exciting. It means that which means it's going to work. This is why the gain used to go up across frequency, because we were basically had a bad cable, which we were capacitively coupled to the input. There must be no connection there. And as you go higher, the capacitance matters less and less. Becomes more and more of a through, and then you get signal. That makes perfect sense. So we can go ahead and increase the frequency, and you can see, indeed, we have enormous gain. This is fantastic. Great, now as I go very high frequency, the SMA is going to start dropping, but this is great. This is a very good sign, which means this one is working. So now let's go ahead and take a look and see what was wrong with that cable. And I wonder if the same thing is happening to the other amplifier and it's actually not broken, the one that had much less gain. All right, and here's the HP one, did exactly the same thing. Let's take a look and see if this one's going to behave the same way or if it has a different problem. So then turning it on and, oh, you know what, plugging it in probably helps. So let's go ahead and try that. And turning it on. Aha, you can see the shape is also quite different. That is also promising. Let's put that into CW mode and 1 gigahertz and on. Ah, that's, whoa, that's a lot of gain. This one has even more gain. So yeah, they work. That's pretty good, which means both of them have exactly the same problem. And what a shame that people would get rid of these things for reasons like that, although this one drops a lot faster. But these things have plus or minus 5 dB or so flatness, so exactly you don't know exactly what you're going to get, but that's pretty good, which means that we have to find a way to connect them to the front and fix the front panel. But I think it's worthwhile looking at those cables to see if we can detect exactly what has gone wrong. And here is an example of how these connectors actually fail. So if you look carefully, you can see that from this joint here where the tip of this connector connects to the not rigid body of the coax, there's a crack, and this crack is more severe. And this one you can see the pin actually getting pushed in. That means that this pin isn't making contact with the next connector over, and of course that's a capacitive connection at that point and no ohmic contact there, and that causes the loss at very low frequencies, which is exactly what we saw. And here we can see some better connectors. These haven't broken. You can see the bend here is the part where it was connecting to the amplifier. That part is not broken because you could absorb the force by just bending a little bit more, but the tip is broken. Now the other connector, here's the inside of what the other connector looks like from the front. I've taken it apart because this one completely broke apart. That's the center pin that goes inside. Now I've already taken these apart in some of the other videos. There are washers, and these are extremely high tolerance devices. And here's the main pin that goes inside, or the main part that it sits on the inside of this like this, and that's just completely broken apart. I couldn't take it apart without totally destroying it because it already had cracked. A good one of the channels was still good, and that's this one. You can see they still together, so I need to find a replacement for this if I want to bring both of the units back to life. But I did bring one of them back to life, and let me show you what it looks like after my modifications. And here's the modified amplifier. I chose to fix the Agilent one simply because it was a newer unit. I have using 2 flexible cables here. These are fairly short. These are actually K to V. I didn't have a K to K connector, so there's a V to K converter here, which is, it's just a huge overkill. These connectors probably cost more than what you would pay for this if you were to buy one from eBay. But I just wanted to get one working for the lab for the time being, until I find a proper cable to replace it. So now we can see if it has gain at 1 gigahertz. That should be pretty easy to try. So here we go. Let me set the source to 1 gigahertz. CW 1 gigahertz. I'm going to turn it on, and there it is. Looks good. Now we have our gain. I can turn it back off, and you will see that the shape here is much better matched at lower frequencies, which is what we would be expecting. So I think it looks pretty good. I will leave this one is fixed, and I can go to higher frequencies as well. You can see it has the flatness. It matches the specification I already tested. It has more than 30 dB of gain, plus or minus a couple of dB, as it is supposed to be. So it looks good. Now the question is, should we bother with opening one of these modules to see what's inside of it? I would like that because I kind of promised that I would show you what's inside one of these. Depends on whether it's destructive to open it or not. So let's go take a look at it outside of the unit. And here's the module outside of the instrument. This is from the HP one, of course, the one that we couldn't fix yet. And you can clearly see very nicely how it is labeled. The biasing of G1 to G4 and D1 to B4. These are normally how these are biased from the outside. Makes it very straightforward to provide biasing for different stages of an amplifier. This is definitely not in silicon, so when we open it we will be able to take a better idea. Now normally they don't solder these to the boards neither, so I've taken the screws off, so we should be able to just snap this guy out very carefully. And these are also very highly EST sensitive devices, especially once the module is out and doesn't have any diodes anymore on the gate biasing or the G biasing, depending on how this is manufactured actually. So there we go. Let's get rid of this. Put this, oh, this is nice. Surprise, it is screwed in. It's not soldered, so that makes it a lot easier to take apart. And here's the main PCB. You can see the biasing network on it. pretty straightforward stuff. So now I can go ahead and take these screws off, and we can take a close look and see what it looks like underneath. Now I suspect that we're not going to be able to see the diodes right away. There's most likely some kind of an RF absorber underneath this, because otherwise you're going to create a terrible cavity and resonance modes and so on inside this module. So I think that that's probably glued, so that's going to be the difficult part to remove, I suspect. There we go. You see, remove all these screws, and there it is. Yep, just as I thought, there is some kind of protection there, so we have to get rid of that. Well, the bad news is that this is a solid piece. It's not one of those flexible RF absorbers that I can just peel off. Breaking this would almost certainly destroy the amplifier, because it's not possible to avoid pieces falling onto the wire bonds underneath. And then if I break this, I won't be able to put it back. And since this is a working 26.5 gigahertz amplifier, I'm really reluctant to damage it. But if you have a broken one and you want to send it in for me to analyze, I could definitely do that. But I didn't want to also leave you with absolutely nothing to analyze here, since I promised to take something apart. So let's take something apart that's a little bit easier and doesn't have as many problems. Now this is a 3.6 gigahertz amplifier. This is also a fully functioning one. It also has a detector output. So it's interesting to see how this detector output is actually implemented. I took this out, I forget from where, some instrument in the past, and it is functioning as well. So I've taken the screws off, and we can take this off, and there's a bottom. Interesting enough, this doesn't have an RF absorber, but if we flip it, we can take a close look inside. I can explain a little bit what's going on. It's a nice, neat design, nothing unusual. You can see it's HP branded, and make sure the camera focuses here. So there we go. So take a look and see what's going on. So here's the input is on this side, and the output is on this side. So if you look at the input, you can see it's AC coupled. At the top, it goes over a diode, most likely for protection. And they have a little line there to tune out the diode parasitics from the input. And then you have 1, 2, 3 stages of amplification. They're all AC coupled from each other. You can see these long lines, these loop lines that are at the bottom. They're all the biasing lines of these amplifier stages at the top. And all the biasing network here is at the bottom. And we go all the way to the output, and the final output of it goes there again, AC coupled into the final output. You have some more matching network there. That's interesting to see. And then they have a coupled line over here, and this coupled line goes into a detector. It's just using the similar diode for detection purposes, and then the voltage out of that detector comes out to this connector down here. So this amplifier is able to tell you how much output is coming from the output of the amplifier itself, because there's a coupled line there. So it's pretty straightforward architecture. Now the difference between something like this and the one I was about to open is that, of course, that one is going to be all integrated circuit space. It's not going to be discrete like this. And it's going to have most likely a single or maybe 2 distributed amplifier stages in a row, and then each individual stage is externally biased. So it would have been interesting to see the inside of that unit, but like I said, I think sacrificing a 26.5 gig amplifier, which is pretty rare to find, is probably not a good idea. But if you do have a broken one of these, or if you still really want me to break it, let me know, and then I can definitely do that. But I hope that you enjoyed this video and got some insight into how some basic failures of cables, even when they're very tiny, can be detected by the frequency response of the amplifier. If you have gain at high frequencies but not at low frequencies, it can be a sign of that. So I hope you enjoyed this. Let me know. I have a really cool video that I'm working on right now to make, and hopefully that will be ready soon, and I'll post that, and I'll see you in the comment section.